Hi, and welcome to section 1.5 for Math 181. This is the first of 3 videos for this section. In this section, we're going to be looking at something known as continuity. So as the name sort of sounds, continuous, that's what we're wondering here. Are these functions continuous? So first, a definition. We say that a function is continuous at a number a if we have the following condition. If the limit as x approaches a of the function is equal to the value of the function at that number a. The easiest way, if you have a graph of a function, to determine whether or not it's continuous is simply ask yourself the following. Do I have to lift my pencil or pen or whatever writing apparatus of your choice? If you're drawing the function and at some point you have to stop and pick up your pencil and put it back down on the paper to keep drawing the function, that is not a continuous function. And what that is called then is the opposite, would be discontinuous. So we have a few different types. The first is what's known as removable. So for example, what this might look like is similar to the following. Some line that has a hole in it. So can I draw this one without lifting my pencil? Well, I can get to this point, but then I have to pick it up for just a second before I continue. That instantaneous lifting and replacing of the pencil makes this not a continuous function. The second type of discontinuous function would be the infinite function. So a graph of this one might look similar to the following. And we've seen this one already, like our 1 over x squared. So this one, from the left side, I can leave my pencil on the paper. It's not a problem. But as I get up to infinity, if I want to continue on this graph, I have to jump over the 0 line and then come back down. So this thing keeps going, and I can never really take my pencil off because it doesn't stop on one side, so there's no way to get to the other. And then the third type is what's known as jump discontinuity. So as the name implies with this one, and we had a similar example here with like the light switch, no power, and all of a sudden turn on the switch and you get power. So that one looked like what? It looked like this at 0, and then you have to jump up here to 1. So you're going along just fine, but then to get to the graph you have to jump to a different height, up or down. A little different from removable, because there it's still in the same sort of line, same sort of movement, but you have to jump for that 1 second. Here you're actually jumping to a different value altogether. Let's look at another definition. So we have the following for definition number 2. A function is continuous from the right at a number a if we have the following. The limit as x approaches a from the right, so we put that little plus sign in the upper right there, of f of x is equal to f of a. So this is just breaking down definition 1 into the from the right or from the left. And so again, so that's, I guess we'll call that A, and then B, a function is continuous from the left if, and then same idea, the limit as x approaches A from the left side, so it gets the little minus sign, of the function f of x is also equal to f of A. Definition 3. So this first video is going to be a lot of definition, just figuring out what are we talking about when we're talking about continuity. So for definition 3, we have that a function f is continuous on an interval if it is continuous at every number in the interval. So that kind of makes sense, right, if we think about that jump continuity picture. So if we had some interval and we're never having to pick up our pencil, then obviously it's continuous in that interval. But if at some point within that interval we have to pick up our pen and move it or pencil, then of course it's not continuous in the interval. So we're not talking, well, we could be, all real numbers. We might be just be looking at whatever, 0 to 1 or -2 to +2. Some specified interval, and it's continuous on that interval if it's continuous at every number in the interval. So let's look at an example. So we want to show that f of x, which is equal to 1 minus the square root of 1 minus x squared, is continuous on the interval, and it's a closed interval, so it gets these brackets, -1 to +1, including those endpoints. Remember, that's what that bracket means to us. So in this situation, we actually have to look at this in two parts. The first part is just between -1 and +1. And then the second part would be actually at those endpoints. And that's using sort of both of these different definitions that we just had here. So can we prove that it's continuous on the interval, and then can we also show that it's continuous at those endpoints? So first, let's look at -1 to +1. So again, if this thing is continuous on the interval, whatever number A we pick, it has to be continuous at that point. So that means what? That means that the limit, if we go back to definition 1, as x approaches A of the function so this means we're looking for the limit as x approaches A, and our function is what? It's 1 minus the square root of 1 minus x squared. So now here's where we're going to use our limit laws. We're going to break this guy apart. So this is the same thing as what? The limit as x approaches A of 1 minus the limit as x approaches A of the square root of 1 minus x squared. So again, one of our limit laws, if we have the limit as it approaches any number of just some constant, well, that's just that value, right? 1. A Again, using one of our limit laws, we can take this inside. So this is the same as the limit, moving the limit piece inside. X goes to a of 1 minus x squared. So we're just applying all these limit laws that we had. I believe it was video 1 for section 1.4. So if we apply this again, we get what? 1 minus, well, the limit as x approaches a of 1 minus the limit as x approaches a of x squared. And again, with our limit laws, this becomes what? Square root. This is 1 again. And then recall, when we have x approaches some number of our function x squared, we can plug that value in. So this really just becomes a squared. So this is what? 1 minus the square root of 1 minus a squared. Well, if we look back to our function, that's what? That's if we just plug in a for x, we get that guy there. So this is really just f of a. If we plug in a to our function, the x becomes an a, so we get 1 minus the square root of 1 minus a squared, which is f of a. So by definition 1, it's continuous on this interval a because our function is equal to that f of a. The limit as x approaches a is equal to f of a. So that's for the interval, but not the endpoints. Our second thing we have to look at is those endpoints. So first thing we want, the limit as x approaches -1, but from which side? So think about this interval. If we have this on the number line here, -1 is here, +1 is here. As I get close to -1 from within this interval, it means what? It means from the right side. So the only way that I can approach, if I'm in this interval, the only way I can get close to -1 is if I'm coming from the right side. I can't approach -1 from the left because I would be outside of the interval. And so I want f of x. So the limit as x approaches -1 from the right side. So this is what? I can plug this in. So this -1 plugged in here. 1 minus square root of 1 minus -1 squared. So 1 minus square root 1 -1 squared is 1, 1 minus 1. So that's 1 minus square root of 0, which is just 1, which is also what? That's equal to, so that's f of -1. So using definition 2, that it's continuous at this point if it's continuous from the right, and we have the limit as it approaches this number from the right is actually equal to that f of a value. And here our a is -1. So by definition 2, this function is continuous at -1, because it's continuous at -1 from the right, which is equal to f of a, in this case, -1. Same thing for the other endpoint, +1. The only difference is we're approaching 1 from which side? Well, now the only way to get towards 1 is if we're approaching it from the left. So we get x approaches 1 from the left of f of x. And again, if we plug all this in, we end up getting 1, which is f of 1. So by the same definition 2, this is continuous at -1, it's continuous at +1, and the first part we showed is continuous at every number within the interval. Therefore, this function is continuous on the closed interval -1 to +1. Last part for the first video here. So if you need any of this, you want to go back, kind of try to follow through, go ahead and hit pause. Otherwise, I'm going to erase this, give you guys theorem 4. And that will wrap up video 1 for this section. So with theorem 4, again, it's sort of this algebraic manipulation of these functions, continuous functions. So we have if f and g are continuous at A, and c is a constant, then the following are continuous at A. So the first one is if we add these functions. Function f plus function g is continuous at A if both of those functions were continuous at A. The difference, f minus g, also continuous at A if the individual functions were continuous. If we have this constant times either one, c or f, that's also going to be continuous. If we have the product, so we take these two functions, we multiply them together, they are still going to be continuous at A. And lastly, the ratio. So if I have the function f divided by the function g, but we have what? We have this function g that's now in the denominator. So g at A cannot be 0, otherwise it would make this guy undefined. So that wraps up video 1. Come on back. We'll look at some examples, a couple more theorems in video 2.